Thank you for attending this web seminar for fast, low-level spurious search with Tektronix real-time signal analyzers. My name is Matt Maxwell, and I am the product manager for Tektronix real-time signal analyzers. By the end of this presentation, I hope you will have a better understanding of the challenges presented by high-performance device transmitter spurious performance testing, such as devices used in satellites, radars, and cellular base stations, as well as some ways to address these challenges. The agenda today is to talk in some depth about these low-level spur searches to gain a better understanding of test equipment performance requirements to perform measurements on devices requiring very low measurements. We will talk about some of the specific testing required on these devices that require a very long time to complete. These long test times can impact development schedules dramatically and can be unacceptable in some cases. Detecting low-level signals in the presence of noise will be explored in some depth, as actual signals can be difficult to see on an instrument screen, such as those within 3 dB of the noise floor. We will then discuss a wideband architecture associated with the real-time signal analyzer from Tektronix, which can dramatically improve these test time speeds. We will then cover one business case example where the Tektronix real-time spectrum analyzer was shown to have dramatically faster test times and therefore continue to keep a development program on track while saving time and money. Like all other transmitter tests, a spur search test determines if the number and level of various spurs from a transmitter are acceptable. For some higher performance devices, this limits on the number and power levels of spurs emitted from a transmitter can be very low. In most cases, a spur search is done over a wide frequency range. In order for a spectrum analyzer to measure these spurs, it is necessary to use every means possible to reduce the instrument's noise floor for measurements. Some examples of techniques include filtering out the main output signal of the device under test to reduce the harmonics and other spurs in the signal analyzer being used. Also using a preamplifier to improve the instrument's displayed average noise level or noise figure, and applying video bandwidth filter or trace averaging to detect signals that are close to the displayed noise floor, and even deploying digital signal processing inside the analyzer to measure and subtract out some of the noise inherent to the analyzer. These methods of improving a given analyzer's noise floor can still cause the instrument sweep time to become very long. This is mainly due to the use of a narrow resolution bandwidth filter done over a very wide frequency span. The sweep time or update rate for spectrum measurements can become very large. To get a sense for how long, the measurement update rate is a function of the inverse of the resolution bandwidth squared for legacy spectrum analyzers. This results in sweep times that can be hundreds of minutes or even longer. For example, over a 20 GHz sweep using a 30 kHz resolution bandwidth filter, the sweep time can be 33 minutes, and this increases as the resolution bandwidth is decreased to help realize the required measurement floor. So these wide bandwidth, narrow RBW spurious measurements may need to be performed over multiple varying environmental conditions. It may be that different measurements are repeated dozens of times, for example. When a failure occurs, the device under test needs to be reworked. The test times can become the bottleneck in getting a high-performance RF product to market. The Tektronix RSA takes a different approach. We will explore this a little more to see how a conventional spectrum analyzer with a narrowband architecture contrasts to the real-time signal analyzer and its wideband architecture. Here we see a simplified block diagram of a swept-tuned spectrum analyzer. The signal path here is the incoming signal is filtered and pre-selected depending on the frequency range. The signal is down-converted, shown in the diagram with the mixer and the local oscillator. The bandpass filter shown is normally implemented using a yttrium iron garnet filter or YIG filter. This serves as a pre-selector for the instrument. The signal is mixed and down-converted to an intermediate frequency, or IF, and then digitized. The digitizer normally has a bit count of 14 plus bits in order to enable high dynamic range performance. The bandwidth of the system is determined both by the analog bandwidth of the IF signal path as well as the sample rate of the analog to digital converter. The remaining part of the signal path is implemented in the digital domain. The resolution bandwidth filter is the next step in the signal path. Like with legacy RF spectrum analyzers, the effective sweep time will be slower when a more narrow RBW is selected. The sweep time is a function of both the effective bandwidth of the analyzer in the IF sense as well as the RBW setting being used. One of the limitations of this architecture is the analog bandwidth of the IF is that most instruments would only use a 10 megahertz IF bandwidth to ensure best performance in terms of image rejection inside the instrument when performing spectrum measurements. Even if the analyzer in question has capabilities to use a wider IF up to 40 megahertz, these instruments still perform spectrum measurements using a narrow bandwidth signal path or less than 10 megahertz. Additionally, most all these instruments' RF specifications like image rejection and harmonics only apply when the instrument is used in the narrowband sense. Using a narrow RBW is essential to perform these low-level noise floor measurements to get the performance needed, but at the expense of slowing down the sweep speed dramatically. As a short aside, we will talk about a few issues around detecting signals in the presence of noise. There are a number of ways modern signal analyzers use to achieve these low-level signal measurements. The first topic here is to look a little more closely at the effect of using a resolution bandwidth filter in a spectrum analyzer measurement. Electrical systems have white noise distribution. When spectrum analyzers are used to measure these low-level RF signals, the wider resolution bandwidth setting results in a higher apparent noise floor because there's more integrated power inside the resolution bandwidth filter. In general, if the RBW is doubled, then the observed noise floor would increase by a factor of 2 or 3 dB. When very low noise floors are required, all techniques possible could be used. This includes adding a preamp and various other noise cancellation techniques. The low RBW is required often as well, and when applied, a low RBW can cause these very low sweep times. Here the effects of using a low RBW can be seen. The same signal is being measured in each of the displays shown. For the display shown on the left, the RBW is set to 1 kHz. With these settings, the minus 110 dBm signal at 1 GHz is obscured by the observed noise floor. When the RBW is lowered to 10 Hz, as seen on the display on the right, the same minus 110 dBm signal at 1 GHz is much more clear. Recalling that the spectrum analyzer block diagram from earlier in the presentation, the 10 Hz RBW does not present the detector with as much noise as the 1 kHz RBW. The RBW has been reduced by a factor of 100 from 1000 kHz to 10 Hz, and therefore the noise is reduced by a factor of 100 or 20 dB. This gives enough margin between the observed noise floor to make the signal viewable. The trade-off here is the instrument sweep time. The measurement example is being performed across a 100 MHz span. For a legacy swept spectrum analyzer, the sweep time would increase by 1 over the square of the RBW or slow the sweep time by a factor of 10,000. This is a significant penalty in the measurement time, and many people would not wait for this measurement to be completed unless they really required such a low noise floor on the measurement. Note that with the real-time spectrum analyzer, there would not be this penalty because of the dedicated wideband architecture, and we will look at more at this later in the presentation. The next issue we will talk about for detecting signals in the presence of noise is trace averaging, or averaging a series of traces. As you can see in the diagram in the lower left corner, the noise floor resulting from a single sweep has enough variability such that the signals within 3 dB of the noise floor are easily confused with the variations of the noise floor. Another way to improve the analyzer's ability to view low-level signals within the analyzer is to average a series of traces. In this case, the screen on the lower right side corner shows the same signal averaged over 5 traces. This improves visibility of the signal, which can be seen at the center of the trace in the lower right. Also, a video bandwidth filter could be used in the instrument, which is the equivalent to performing a non-integer value of averages. The Tektronix real-time signal analyzers can use a video bandwidth filter as well, with patented DSP techniques to copy the behavior of this analog VBW on a measurement. An important concern here is to pay attention to the type of averaging being used. When the concern for measurements are CW-type spurious signals, the average of log power can be used. This converges to a value of minus 2.51 dB lower than other methods. However, when measuring noise-like signals such as CDMA type signals, the measured average power level will be minus 2.51 dB lower than the actual value. For noise-like signals, the average of linear power must be used. Many of today's modern spectrum analyzers are hybrids between analog superheterodyne and digitally implemented analyzers and use fast Fourier transforms, or FFTs, regularly. FFTs are useful as they can help speed up measurements that using analog hardware in legacy spectrum analyzers. The RSA is also an FFT-based instrument, and many signal analyzers on the market use FFTs automatically even in narrowband measurements using a 10 MHz IF signal path. So it's important to understand how the number of FFT points can relate to the RBW used. For this example, we will examine how much a measurement's observed noise floor would increase as a result of the limitation of FFT points for the desired RBW. This is an effect seen when using a plus peak detector. For the example, consider a case of a 100 MHz band measured with a 10 Hz RBW. If there are 2 FFT points per resolution bandwidth, more than 20 million trace points would be required. In this example, if the display has only 99 points, this would be an insufficient number of trace points. Modern spectrum analyzers can show between 10,000s to hundreds of thousands of trace points. In the table at the bottom right of the page, that as the ratio of the RBWs to trace points increases, the reported dB rise in observed noise floor increases. This is based on the number of standard deviations that would be present with a plus peak detection when measuring noise with a Gaussian distribution. Those last few slides talked about issues to be concerned about when performing measurements of signals in the presence of noise, or signals that are close to the noise floor. Now to focus on the difference of the Tektronix real-time spectrum analyzers, we see a block diagram that's describing how the Tektronix real-time signal analyzer takes a different approach from conventional spectrum analyzers. The key difference here is the wideband architecture employed. The RSA needs to work in a wideband mode all of the time to enable some of the unique features, like the very fast FFT update rate and some unique frequency selective triggers. The architecture digitizes a 110 MHz bandwidth at all times, whether this is stationary at a fixed frequency or sweeping across the 20 GHz frequency range of the instrument in steps. For swept measurements, the RSA does behave like a normal swept-tune spectrum analyzer. FFTs are performed in steps across the frequency range when they are greater than 110 MHz bands set and desired for the measurement. The resulting speed for wideband spectrum measurements can be much faster when a low resolution bandwidth setting is required because the instrument can perform an FFT across a much wider bandwidth of spectrum and display those on the screen. We will have one specific example of the improvement in sweep speed in the coming slides, but there is very little measurement speed penalty when using a narrow RBW measurement filter. Here is a comparison of the measurement performance between a legacy swept-tune spectrum analyzer and the RSA6100B for a 20 GHz sweep. If a 10 kHz RBW is used with the internal preamp turned on, the measurement's observed displayed average noise floor is minus 110 dBm. The sweep time for the legacy analyzer is 294 seconds, compared to a sweep time of 15.3 seconds, achieved with the same settings on the Tektronix real-time signal analyzer. This dramatic improvement in sweep time is achieved when a wideband acquisition bandwidth is used in the RSA, as described previously, and has fully specified performance when operating in this way. Additionally, the RSA does have the same traditional spectrum analyzer controls discussed previously, like video bandwidth, trace averaging, and a selectable number of trace points, markers, and detector selection. One of the unique capabilities of the RSA is swept DPX. This allows the instrument to examine 110 MHz bandwidth of spectrum at a time to achieve a wideband sweep of the entire 20 GHz frequency range. The DPX capability is powered by a dedicated FPGA where the instrument's real-time capabilities are enabled. The FPGA performs at a rate of over 292,000 FFTs per second and can display them in a number of ways. Here we show a 500 MHz sweep using DPX, where 100 MHz steps show 50 milliseconds worth of data in each step of the FFTs displayed in a bitmap form with color grading. This means the bitmap represents over 14,600 FFTs, or about 292,000 times 50 milliseconds per step in this fast sweep mode. Also, the thin yellow trace shows an average of those 14,600 FFTs. This fast trace averaging capability shows clearly that there are lower level signals being measured. In this case, a signal over the air is being measured, so near the right edge of the screen, the 2.4 GHz ISM band can be seen with several signals present, including a wireless LAN signal. The benefit of this capability is when fast averaging and additional insight into the signal behavior is required, DPX or swept DPX with this averaging capability can dramatically improve the speed of averaging and therefore the ability to find some low-level signals in the presence of other signals. There are various specifications to consider when considering a spectrum analyzer's performance for these kinds of low-level spurious measurements. It is important to consider most all of these areas when performing these measurements. Harmonics are signals that appear when an analyzer is tuned to n times the frequency of the signal present and are produced inside the analyzer's intermediate frequency conversion chain. These signals are not present at the input of the analyzer. For the RSA5100B, the second order harmonic is the most relevant with a specification of -80 dBc. For other analyzers, the third order harmonic or second order harmonic may be the most relevant. This depends on the designs of a particular IF architecture and the frequencies used in the down conversion chain. Spurious due to signals are a result of the interaction between the signal present and the various elements inside the instrument. These are relative to the maximum input signal present. These are also signals that are not present with the input signal but are generated inside the IF signal chain and are a function of the input signal and the various local oscillators used to downconvert the signal. The residual spurious signals are different from the harmonics or spurious due to signal, as the residuals are not a function of the input signal. Rather, these are present when the instrument's input is terminated. The specification for the RSA6100B is -90 dBm for these residual spurious signals. When performing low-level spurious measurements, it could be important to consider all of these specifications depending on how the measurement is being performed. For example, when the input signal can be attenuated, filtered, or otherwise removed from the input to measure only signals outside of the input signal, the residual spurious performance can be the most important of all of the parameters. While instrument performance on the RSA6100B cannot be guaranteed beyond published specifications, it is important to understand both specifications and the mechanism for a particular signal to know what produces it. For example, if a harmonic is observed, it would be good to know that this is coming from the instrument or if this is coming from the device under test. And that would be a function of the frequency of the input and the IF signal chain being used. Let's take a look at a real-world example of the benefits that one company had who switched to using the RSA6120B. This was a U.S. DoD contractor who had been using legacy spectrum analyzers for a number of years. There are a number of tests that the spectrum analyzers were used for, but the longest test in the validation and manufacturing and engineering process was by far the spur test. The requirements for these tests were beyond the specified performance levels of all the analyzers available, so additional steps were taken to make sure the instruments could be measured, or the instruments could be used to perform the measurements. For example, the main signal from the device under test would frequently be attenuated to measure only the spurs produced by the transmitter. Reason for the length of the spur test was a low resolution bandwidth used for spur measurements was used and repeated over varying environmental conditions. With each spur measurement taking hours, it could take weeks to complete an entire set of environmental measurements assuming no rework was required. When failures occurred and reworks were required, this could drive the total test times to be greater than a month per device. Clearly, this drove the cost very high as it required more equipment and time to complete these tests. The RSA6120B was benchmarked by this company and found to be much faster. This is because of the RSA's wideband architecture used when performing low-level, low-resolution bandwidth measurements. The RSA was nearly 6 times faster than the next fastest spectrum analyzer that was considered. Because the testing included measurements performed over varying temperatures and pressures, the total test times were reduced by hundreds of hours. This savings in test time easily justified replacing the test line with RSAs. The RSA's combination of wideband architecture and high RF performance met the testing needs for this application. Thank you for attending this webinar about fast, low-level spurious measurements using Tektronix real-time signal analyzers. During this presentation, we looked at test challenges associated with performing these low-level measurements. Low-level measurements would be performed on high-performance devices such as satellites, radars, and commercial base station power amplifiers. There was a description of how these measurements would be made with a conventional spectrum analyzer, specifically how these instruments run with a narrowband architecture leading to long test times if a narrow resolution bandwidth was required to perform a measurement. There was a description of some key points on how low-level signals would be measured in the presence of noise and the resulting spectrum settings and plots that go along with these measurements. We introduced the real-time signal analyzer from Tektronix as an alternate tool for performing these kinds of measurements. The Tektronix real-time signal analyzer performs the same spectrum measurements as conventional spectrum analyzers, but use a wideband architecture which dramatically improves the measurement speeds when these low-level measurement levels were required a low-resolution bandwidth filter, resulting in much faster test times. There was a discussion about how different spectrum analyzer specs were important to consider when performing these measurements, as well as a description of how the RSA5000 series did in these different categories. The key specs discussed were harmonic performance, spurious with signal, and residual spurious performance. Additionally, there was a discussion on what was important to consider when performing these measurements outside of the published specifications. Last, we covered a real-world example of a company using a Tektronix real-time signal analyzer, and that was able to save them time and work in one of their most critical test paths, low-level spurious measurements. This results in test time that was orders of magnitude faster than the legacy analyzers, and this company was able to perform these tests much faster than even the next generation spectrum analyzer they were evaluating by using the Tektronix real-time signal analyzers.